Okay, so we're going to talk a little bit today about eyes and about how they receive light signals and send it to our brain cells. Okay, here we have a classic build for our for receiving light with some photoreceptors. Receptors, which would be these little building-looking things here. And we call these the surround and the on-center cells. So this would be, we're going to be talking about the on-surround, off-surround, on-center style. So here we have horizontal cells that are able to connect the outer photoreceptors, the inner photoreceptors, which will allow them to send signals to this, which is known as the bipolar cells. And these send signals here to the ganglion.
Ganglia cell.
Ganglia cells, which sends signals to the brain. Okay. And so, let's talk about what happens if light hits the off-surround cells or photoreceptors. So when light hits here, it's going to cause an activation in something known as G protein coupling receptors. So these G protein coupling receptors are going to increase in amount, which is gonna, or it's gonna activate it more, which is gonna activate the PDE, which is an enzyme here that likes to eat something here known as cyclic GMP. Now, what does cyclic GMP do? Cyclic GMP opens the cation channel here, and the cation channel allows for calcium to come in and out, or to come into the cell. And so with less GMP here, that means the cation channel is going to be open less, which means it's going to be less calcium coming to the cell to activate or to cause. This is a vesicle that releases something known as glutamate. And glutamate is an enzyme or a neurotransmitter that is used here a lot in these reactions. And so, with less calcium means it's going to be less glutamate released here into the horizontal cell to something known as AMPA. So, when there is less glutamate coming in here, that means there's going to be less activation in the AMPA. Which is going to decrease the activation of the other channel here known as the GABA. And so since these are both decreased, it's going to, here we have a chlorine channel.
What is GABA's job?
GABA's job is to open the chlorine channel.
Okay, does it GABA makes the IPSB or EPSB?
It makes IPSB.
Okay, can you write the IPSB?
Yeah. So since there's going to be less GABA being activated, there's going to be a decrease in the IPSB, which means the chlorine channel will not open. It will not have chlorine come in as much, which is going to increase the amount of calcium in here, which is going to increase the amount of glutamate here again.
Okay, please explain the between the chloride channel and increase of calcium, what happened?
Yes, so chlorine's job is to hyperpolarize the photoreceptor, which means it's going to decrease the RMP and decrease the amount of calcium that's able to work inside.
Able to come inside the cell.
Come inside the cell and do its job. So with the decrease in the amount of chlorine we're going to be able to see more calcium come in and depolarize in the cell, which is going to cause more release in the glutamate neurotransmitter into here to the bipolar cell. Now here we have another channel known as the mGluR6. When the mGluR6 receives a lot of the glutamate here, it's going to activate and it's going to close this channel here. Now this channel here is known as the TRMP. TRPM, sorry.
1.
TRPM1. So TRPM is going to close, and that causes causes less glutamate here to be released. So as you can see, these little circles are glutamate, vesicles containing glutamate. So with less of the glutamate here, there's going to be less coming in here to the channel here, which is in the ganglia cell, which means the brain is going to receive less action potential, telling it it's dark. And so what would happen if we do now the opposite? Instead of light receiving in, it stays dark. Sorry, I forgot to put light here. So if it's dark here, it's going to cause a little bit of an opposite reaction. So the G protein coupling receptor is going to be activated less, which is going to activate less PDE, which is going to allow for an increase in the amount of cyclic GMP binding to the cation channels and opening them up, which means calcium is now going to be able to come into the cell or into the photoreceptor more readily, which means it's going to bind to the vesicles and release glutamate more. And so with more glutamate being released to the horizontal cell, that's going to cause the AMPA to increase. It's going to cause the GABA to increase, which is going to cause the IPSP to increase, and it's going to allow the chlorine channel to open more and hyperpolarize the cell, or the photoreceptor. And once the photoreceptor here is hyperpolarized, that's going to cause less calcium to come into the cell, and there's going to be less of a release of glutamate here, which is going to activate the mGluR6 less. And now that the mGluR6 is less activated, that's going to allow the TRPM1 to stay open. And that allows for calcium to come in and for more glutamate to be released here from the presynaptic bipolar cell to the postsynaptic ganglia cell. So now with more glutamate means that there's going to be more action potential going to the brain here.
Where is the postsynaptic of the bipolar cell?
The postsynaptic of the bipolar cell is here, in this area right here. It's where it receives the neurotransmitters coming from the presynaptic photoreceptor cell.
Which photoreceptor is physically, not physically, kind of connected to the neuromuscular junction connected to the bipolar cell?
Yeah, that'd be the on-center photoreceptor cell. These are not connected to it. They have to send the signals via the horizontal cells to
the on-center
photoreceptor, which sends the signal to the bipolar cells.
Okay.
So now let's talk about what's going to happen if light hits the photoreceptor in the center here. So if light hits here, here we have a similar setup here with our G protein coupling receptors. We have our PDE, and we have our cation channel. So, and we have cyclic GMP. If light were to hit here, that's going to cause increase in the G protein coupling receptor, as we saw here.
Activate the G14 coupling
Yeah.
receptor.
It's gonna activate it more, which is gonna activate the PDE more, which is gonna decrease the cyclic GMP, which is gonna decrease the cation channel opening, which means there's gonna be less calcium coming into here.
So is it what's how the cell changes? Cell RMP changes. Is it hyperpolarized or depolarized?
It's gonna be hyperpolarizing because there's gonna be less calcium coming in, and there's gonna be less depolarization. So since less calcium is in, that means the glutamate here, vesicles, will release less glutamate.
Okay. Sorry. Okay. So question is hyperpolarization makes release more glutamate. Is it true or false?
False. Hyperpolarizing means less glutamate will be released, and depolarization means more glutamate will be released.
How hyperpolarization releases less glutamate?
Hyperpolarization causes a less release in glutamate because it's going to cause less calcium to come into the cell.
How?
Through having a lower RMP means that the gradient of the cell will have calcium not come into here,
okay.
or not
Calcium, the voltage gated calcium channel, they would not be activated because our RMP is low.
Yes.
Yes.
And so, as we said, there's going to be less glutamate activated, or less glutamate being sent to the mGlu6.
Okay.
And so that's going to cause the mGlu6 to activate less, which means the TRPM1 will be more open, which means it's going to be an increase of the glutamate being released here to the ganglion cell.
Yes.
And so that means that the action potential being sent to the brain is going to be higher than the ganglia cell.
So our brain interpreted that
as light.
There is a light.
Yeah, so the more action potential that's being sent to the brain, the more our brain thinks that there's light. So when the light hits the off surround, it's gonna say that it's dark from what we saw. But when dark hits the outside or light hits the inside, it's going to say that there is light.
I want to change mGlu6 to AMPA, and what will be happen?
So if we get rid of the mGlu6 and have that become AMPA, it's going to change a couple different things. As we saw here, when there's more glutamate being released here, there's going to be an activation of an AMPA, which the AMPA is tied to the TRPM1. So if there is, let's say, there's going to be more glutamate coming here, that's going to cause an increase in the AMPA, which is going to allow the TRPM to stay open, which means that our brain there's going to be more glutamate coming down to the ganglion cell, which means our brain is going to see that as light or action potential increase. But let's say there's less glutamate being released here. Since there's less glutamate being released into the AMPA, that's going to cause the AMPA to decrease in the usage, which actually is going to close the TRPM1, and that's going to cause a decrease in the glutamate being released into the ganglia cell, which is going to decrease our action potential, and our brain will think that it is dark. So it's going to cause a little bit of a reverse of the system that we are to know.
Yes. Okay. So we call the AMPA as an inotropic channel. Inotropic channel means it makes excitatory.
Yes.
So any inotropic channel, it makes release of neurotransmitter or calcium increases. Yes. So AMPA is the one type of inotropic channel that increase the release of glutamate.
Yes.
Yes. Do you want to give more explanation? What is off center? On surround and off center.
Yeah, so if we were to go with an on surround here,
And then
and we have an off center here,
and all the reaction, all the process will be
they'd be
totally
completely switched.
opposite.
Yeah, because right now we're looking at off surround, on surround. I mean on center, and so this is what we're to happen if we have light wanting to come into the on center and darkness in the off surround. But if we were to switch it to want on surround and off center, it would completely swap this whole system that we just set up.
If the darkness, if the no light
Yeah.
on the off center,
hmm
would there be action potential?
If we're on surround or off center, if
Off
we're off
center
center and
that has no light.
has no light, there will be action potential.
That's great.
And if light hits an on surround, there will be action potential. But if there's darkness in the on surround, it's gonna be no action potential. And same for on center or off center. If light hits the off center, there's gonna be no action potential being created. Thank you.